All right, dear Heavenly Father, we just thank you for the day. I thank you for the blessings you've given us. Thank you for the students here. Just pray you help them in their classes, Lord. Just guide them in everything we do. In Jesus' name, amen. All right. So yesterday we talked about properties of derivatives. You'll be working on some homework with that tonight and tomorrow. So
What do you mean by properties of derivatives? Like the rules?
correct.
Oh, the rules.
Oh, yes, you did.
Okay. So today we want to talk about rates of change.
Isn't that a slope?
What's that?
Isn't that a slope?
That is a slope. Very good. Excellent. That was my next question. We're dealing with slope. And we find slope by finding the tangent line. Slope of the tangent line. And we find the slope of the tangent line by using
The derivative.
the derivative. The derivative.
Wait, haven't we learned this already?
Basically, we're going to apply it. So if we take a look at page 135. Look at number 2. Write the area of a circle as a function of the circumference. Write the area of the circle as I misread it here. Write the area of a circle as a function of the circumference. What? Area equals pi r squared. Circumference equals 2 pi r. Alright, so this is the area in terms of the radius. This is the circumference in terms of the radius. We want the area in terms of circumference. So I gotta get rid of radius and get in C. So how I do that, I'm gonna solve for r and substitute it in. So now I get A equals pi times C over 2 pi squared. I had markers that actually work.
Okay, that makes sense.
So now I'm going to simplify. A equals C squared over 4 pi. And that's what they want for the first one. They're going to tell you, I want this function in terms of this variable. So they say we want the area in terms of circumference. So we had to get rid of the r. Next thing they asked, find the instantaneous rate of change of the area with respect to circumference. Well, if they want the instantaneous rate of change, they're asking us for what?
Slope. Right?
Well, yes, but
The derivative?
derivative. So now I'm going to take A equals C squared over 4 pi and take the derivative, so that's dA, so that means I took the derivative of A in respects to circumference, dA over dC. So this is the function I took the derivative of, and this is the variable that is in respect to. What's the derivative? That's going to be C over 2 pi.
Oh, because it would be 2c, and
Yeah,
then
right, you're gonna take the 2
cancel out.
and multiply, so that's really 2 times C over 4 pi.
Okay.
The 2's cancel out, so now I have C over 2 pi.
And that's the,
That is the rate of change, instantaneous rate of change. They say evaluate the rate of change of A at C equals pi. So you're gonna put pi in. Which I get 1/2.
You found the derivative, C over 2 pi from the low d minus the high d over the.
So they say, for this here, so every time the circumference changes by 1, the area changes by the circumference divided by 2 pi. So when I put the pi in, the circumference changed by pi, or at pi, the area is going by a half. Alright? Because again, what's my units? Circumference is in inches over x, y over x. Inches squared over inches is my units. Because remember, if I have y equals mx plus b, what's my slope? What does my slope represent here? Rise over run, right?
Yeah.
Y over x, right? So here, what's my slope represent? Y over x. What's my y? Area. How do I find area? Inches squared over circumference, because my x here now is c. And what's my unit? Let's c, inch. So for every inch the circumference changes, the area changes by this value. So for every inch the circumference change, the area is changing by 1/2. Okay?
Can you explain where you got, I mean, I know how you got, inches squared over inches, but where did you start to get it?
Well, again, knowing what slope is. Slope is rise over run. What's my rise? Well, in this form, my y is a, capital A, area. My x is c. So it's area over circumference. What's the units for area?
Inches squared.
Alright, or unit squared. And what's my units for circumference? Just units. Alright, which is inches. Alright, so when my circumference is pi, my area is 1/2. Alright, when my circumference is 6 pi, my area is 3.
So that's from, the, circumference to the rate, or circumference to the area, and then inches squared over inches is the slope
Correct.
of the change.
Whoa, what happened there? Like somebody died. Honestly, actually, the best thing. That's what happened.
I'm not dead.
When you're watching the debate,
Hmm?
when you're watching the debate,
Oh, I saw part of it.
Did y'all see the,
I-
slide that was on Pence's head?
You just sit down
He was there for 2 minutes.
just chilling.
Alright, number 4.
I always saw the very end.
A square of side length s is inscribed in a circle of radius r. Alright, draw yourself a picture. Here's my circle. Inscribed means it's on the inside.
Okay.
The side is s. The radius of the circle is r. Number 4. Write the area of a square as a function of the radius r of the circle. Alright, the square, area of the square is s squared. Correct?
Yes.
Yeah.
Area of the circle equals pi r squared. They say, write the area of the square as a function of the radius r of the circle. Well, we don't need this really. I just need to find a relationship between r and s. Relationship between r and s. If I take this and extend it, what kind of triangle do I have there? Right triangle. It is isosceles as well, because this is s. How can I relate s and r now?
You could use the area of the triangle function times 2, and you take the square root of that, and that would be side S, correct? Wait, that doesn't make
Forget
sense.
Yeah, I have no idea what you're saying. I have no idea what you're saying.
R squared equals the square root, I'm sorry, R squared equals
A square plus
S squared plus S squared. Pythagorean theorem,
Okay,
alright?
sure.
Although this is
It would
really
be 2R squared.
2R squared.
Oh, yeah,
So
that
it
was
would be
not okay.
4R squared.
Did we just figure everything? We didn't even know these?
I thought, I'm sorry, yeah, 2R, it's right here,
That was our fault.
2R squared, there we go. So we simplify, we want to get rid of the S, so we're gonna solve for S, so that's 4R squared equals 2S squared. S squared equals 2R squared. So S equals the square root of 2R squared. Correct?
Oh, wait, that's right. The hypotenuse of the right.
So we put the S back in for the S, so my area of my square in respects to my radius, which would be
2R's.
the
Well,
the
what did
square
we-
root of 2R squared squared
Yeah.
would be 2R squared. So there's my formula.
And that is the area of the triangle. I mean,
That is the area of the square
square.
using the radius of the circle, and not the side. So it doesn't matter what size circle I have, I can always find the area of the square that's inscribed in the circle by using this formula. Take for instance, if I have a circle that has a radius of 5, the area of the square that would be inside that circle would be,
Oh, wait.
if I had a circle that had a radius of 5,
Okay.
using this formula, the area of the square that's inside that circle would be what?
50?
50. Just put 5 in for R, 50 square units. And I don't have to try to figure out what the side is of the square, because it's always going to be this. So here they say, okay, find the instantaneous rate of change of the area with respect to the radius of the circle. So again, we're going to take the derivative of A, which is dA, and what variable am I taking the derivative of?
S.
R.
R. So dr equals
Oh.
4R.
4, yeah.
4R. So that means every time the radius changes by 1, the area is going to change by 4. Okay, so it's going to be, so that's my instantaneous rate of change. 1, area changes by 4. 1, area changes by 4. Second statement says, find the instantaneous rate of change of the area, evaluate the rate of change of A at R equals 1. So we put 1 in, dA over dr equals 4. Then go on and say at 8. dA over dr equals 32. So if the R is measured in inches and A is measured in square inches, what is the units for my slope? Again, is area over radius. Area is inches squared. Radius is inches. So my rate of change is square units over units. For every unit my radius changes, my area is going to change by area squared. That's basically what it's talking about.
Okay.
If we look back at page 127, look on page 127. So if we look at the solution on the enlarging circle down below, down the paragraph, it says, notice that the rate of change gets bigger as R gets bigger. The bigger change in area, so as the circles grow, so as the circles grow radically away from the center. So this is telling me my rate of change. 4 units. But you see, as I get bigger, I went from 1 to 8 as far as my radius was. My area went from 4 to 32. Alright, so it's actually increasing 4 times as fast is the area. Alright, so we're talking about instantaneous rate of change. Alright, flip back to page 135. Let's look at number 6. In exercises 5 and 6, the coordinates S of a moving body for various values of t are given. Plot S versus t on the coordinate paper and sketch a smooth curve to the given points. Alright, I'm not worried about that. Assume that the smooth curve represents the motion, estimate the velocity at t equals 1, t equals 2.5, and 3.5. Now I don't want you to do that. I don't want you to do the group activity, so let's flip over to page 136. Page 136. Page 136, number 10, particle motion. Particle P moves on the number line shown in part A. The accompanying figure, part B, shows the position of P as a function of time. Alright, so the particle is moving along the number line like this. Okay? When is P moving to the left, when is P moving to the right, standing still? And again, rate of change, my rate, if I have a positive rate, I'm moving right. If I have a negative rate, I'm moving left. Correct? So if I'm moving positively, I'm usually moving right. If I'm moving negatively, I'm usually going backwards. Alright? So that's rate. Usually what rates are, positive, negative. So when I look at the graph, if I'm positive, that means I'm doing what? What's that? Going to the right. If I'm negative, that means I'm doing what? Going backwards. Okay? So here it says, when is P moving to the left?
From 2 to 3 and 5 to 6.
From 2 to 3 and from 5 to 6. When is my moving to the right? 0 to 1 and that's it. When am I standing still?
1 to 2 and 5.
Okay. Graph the particle's velocity and speed were defined. Alright, so let's do that. Alright, this pen is terrible.
Whoa. That's white. Got special stuff.
Got the water that was spilled off.
That's what it is, actually.
I think it does something, but it does.
I'm the head of the conspiracy theory. But it's all politics.
Alright, that's better. I don't use that pen anymore.
How
Alright. So, here's my graph. Alright, from 1. What's my slope?
1.
Is
No,
it?
it's not, it's 2.
It's 2.
I didn't see the 2.
From 1 to 2, what's my slope?
Zero.
Oh, no, it is 0.
0. From 2 to 3, what's my slope?
-4.
-4?
No, negative 2. Oh, wait,
Y is in 2s.
not even.
Yeah, it's negative 2.
-4?
Right.
From 3 to 5, what's my slope?
0.
-2. Oh. Sorry, I just can't read.
0, correct? 5 to 6 is what's my slope?
Negative 2.
Everybody agree? -2? So we're here. So there's the graph of my derivative. Okay? Look at number 12. Number 12, it says a racehorse is running a 10 furlong race. As a horse passes each furlong marker, a steward records the time elapsed since the beginning of the race, as shown in the table below. How long does it take the horse to finish the race?
135 seconds.
Everybody agree? 135 seconds. You with us, Connor?
Hmm.
Number 12. Other page. You're good?
Yes.
Alright. What is the average speed of the horse over the first 5 furlongs? What's the average speed over the first 5 furlongs? How do we find average speed?
Add it up and then
Divide.
divide it.
Okay?
So F is the marker.
How many furlongs did we go?
Speed is the feet.
5.
Feet per second. So 5. And how long did it take us to get there?
73.
73. So it's 5 over 73, correct? My units would be what?
Furlongs per second.
Furlongs per second. What is the approximate speed of the horse as it passes the 3 furlong marker?
Wait a minute. I thought we were finding the average.
Well, letter B was the average.
It was 5 over 73?
Mm-hmm.
It was?
How many furlongs did we go? We went 5 furlongs. How long did it take us to get there? 73
Oh,
seconds.
I thought it was asking us what, like, the average speed, like, throughout the whole thing.
No, just for the first 5.
Okay.
It's like 0.0645.
For what?
The average.
Oh, 0.068.
Yeah.
Correct. All right. What is the approximate speed of the horse as it passes the 3 furlong marker?
46. Oh, the speed is 3 over 46.
It's 0.065 furlongs per second, right?
All right. So they're looking for the approximate speed of the horse as it passes the 3 furlong marker. What are we looking for?
This,
The average?
The average.
It's a,
We're looking for the
exact.
instantaneous speed.
Right. Yeah.
Instantaneous speed. Well, how are we going to find the instantaneous speed here?
Can't you just divide furlongs per second?
What's that?
Can't you just divide furlongs per second?
By?
Can't you divide furlongs by seconds to get furlongs per second? I don't get what you're asking.
Was my average is 5 over 73. I want to know the rate at 3 furlongs.
But isn't they're asking for, in letter B, what is the average over all 5 of them, not just at 5? Right?
Over the first 5 furlongs. What's my average for the first 5 furlongs that I did?
Wouldn't you have to, like, add them all together and leave the average?
No, because you don't add them all together because you didn't go 3, 6, 10, 15 furlongs. You just went 5 furlongs. So you had a marker every furlong.
Mhm.
Marker 1, marker 2, marker 3, marker 4, marker 5.
They've
Started
already,
at 0, and I hit furlong, marker 5. How many furlongs was that?
5.
5. Alright, how long did it take me to pass that 5 furlongs? 73 seconds. Distance over time. So 5 over 73 would be my average speed.
Be the average, cause it was
They've
over the
already-
whole time. Like 73 is the whole time you were going. And
cause every distance was 1, and they've already added them up. Like in between 0 and 1 is 1, in between 1 and 2 is 1, and they've added them up to 5.
Okay. That makes sense.
Okay?
Yes.
Alright,
Okay.
so what is the approximate speed of the horse as it passes the 3 furlong marker?
So we have to do x plus h.
Well, the 3 furlong marker is where?
It's
46.
At 46 seconds.
It's in between though, right? Somewhat?
like between.
Oh, 3 divided by 46? It's 0.065.
Alright, so that's fine. What's the slope between 0 and 1?
1
Very
over
good.
20.
Number 12.
1 over 20.
What is it?
1/20th.
1/20th? Alright, what's the slope between 1 and 2?
1 over 13.
So it keeps getting.
What's the slope over 3 and 4, 2 and 3?
1 over 13.
1 over 20, 1 over 13,
It does get bigger.
1 over 13. What's the slope between 3 and 4? 1 over 13. What's the slope between 4 and 5?
1 over.
14.
No.
Yeah.
Oh, yeah.
1 over 14. So what's my approximate speed at furlong 3?
1 over 13.
Oh, I was.
Oh,
Correct.
well, yeah, sorry.
Right? Alright, it says, during which portion of the race is the horse running the fastest?
Well, it
So
would
is
be
that
when.
each step to find all of them?
What's the slope between 5 and 6?
1 over 14. No. 1 over 13.
1 over 13?
So the fastest would be.
6 and 7.
1 over 14.
1 over 14. 7 and 8.
1 over 12.
8 and 9.
1 over 12.
9 and 10.
1 over 11. This guy was not a good horse racer.
Alright, so where's it moving the fastest?
The last one.
1 over 11 is the bigger number, correct?
Yes.
Alright, then letter E, during which portion of the race is the horse accelerating the fastest?
That would be at the very beginning, from 0 to 1, right?
1, right?
Correct.
Right in between
Oh, wait.
0 and 1.
Wait, accelerating fastest.
Yeah.
Oh,
that makes
no,
sense.
would it not?
Well, yes, because from here to here it's going,
Oh, I was thinking maybe here.
right?
Thinking
Are we getting bigger or smaller here?
getting bigger.
Getting bigger? How much bigger?
By
By 7?
yeah.
Alright, same by one, same as one, alright? So we accelerate faster here, because we're going from 0 to 20. Correct?
Yes.
Okay. So that's what they're doing there. Look at number 14. The equations for free fall near the surface of Mars and Jupiter, S in meters and T in seconds, are Mars equals S equals 1.86 T squared, Jupiter equals 11.44 T squared. How long would it take a rock falling from rest to reach a velocity? Okay, so let's talk about velocity.
Where are we?
14.
We got position, we got velocity, and we got acceleration. Thinking about my rates of change. If I have position in terms of, let's just say I have position in terms of time. So where am I at a particular time? So let's say, what do I want to use? I guess I'll use y equals t. If I take the derivative, I get dy over dt. Well, dy over dt now is what? Position over time, which is what? Distance over time, which is what?
Acceleration.
Distance over time is velocity. If I take the derivative of my velocity, that's dy over dt squared. Distance over time squared is what? Acceleration. So if I have a position equation and take the derivative, I get velocity. If I have a velocity equation and take the derivative, now I get acceleration. Okay, so a lot of times position is using an S. So in this case here, they gave us S equals, on Mars, let me find it again, 1.86. So if something's falling in Mars, I can find out my position according to the time. So if at 1 second, where am I at? 1.86 meters. At 2 seconds, where am I at? 1.86 times 4, and so on. They're asking us, how long would it take the falling rock to reach a velocity of 16.6 meters per second? So I need velocity. So what I need to do, I need to take this and make it velocity. So I take derivative. ds over dt equals 3.68? No, 78. T. Correct? So now I want to find out, okay, where is my velocity? Where am I at again? Where is my velocity? About 16.6 meters per second. So I'm going to say 3.78 t equals 16.6. And I solve for t. Well, when I divide by 3.78, what do I get? .6 divided by 3.78.
It's 4.39.
4.39 seconds. Alright, do the same thing on Jupiter. S equals 11.44 t squared. My derivative would be what?
11.44 times 2
So that'd be 22.88 t. Alright, so when will it on Jupiter be 16.6? we'll take. 0.726 seconds. So what we need to remember is position, derivative is velocity, velocity, derivative is acceleration. And we use those concepts to actually do some of these problems.
Taking the derivative of the position.
Correct. So if I take the derivative of position, I get velocity, ds over dt. If I take the derivative of velocity, I get acceleration. Acceleration, if I do it again, take for instance, here, ds over dt squared would just be 3.78. So that means I'm following 3.78 meters for every second per second. Is acceleration. So we'll look at some more of this on Monday.
Okay.
Alright? So you're going to try to do, I don't know, I'll have you try to do that or not tonight. Alright. Don't worry about homework tonight. I will have an assignment for you to do in class tomorrow, and then we'll go over it on Monday. Okay?